This is Møller Nielsen from Geeks, and I'm going to teach you how to write clean, efficient code using machine learning. Now, if you have always wanted to know the difference between artificial intelligence, machine learning, what kinds of types of machine learning there are, then this video is definitely something for you. Complementary to this video, there will be related articles and links in the description below. Please take the time to like, subscribe and hit that notification bell so you know when we have the next video coming up. Now, without any further ado, let's get started. So there are some concepts that are very often mixed together when we are talking about machine learning, artificial intelligence and also neural network. First of all, artificial intelligence, it just means that we are imitating human behavior. So that means that actually any program that you can write, any machine you can create, that actually it seems like it can actually trick people into almost recognizing this program or this robot into being something that is actually human. Then you have actually written artificial intelligence. Pac-Man is a good example of this, and I will show you an example in just a minute. Then we have a subfield of this, and that is the machine learning. The machine learning is when we take something very, very complex. So we have some input variables and we have some outputs, and then we can try to build a model so we can actually predict when we get a certain set of input, and when we have a certain set of input, what kind of output would we get, even though that we do not know an exact formula to calculate this. Then we can use something called machine learning, and we can actually we can train our model so it actually becomes smarter over time, and it can actually self-correct itself if we have something called reinforced machine learning. But there are three different types of machine learning. One of them is the supervised machine learning. This is where you would actually you would train the model. You would have a huge amount of data sets. So it is always it always depends on the data set how good your model is. So you need a lot of data, and then you will take maybe you will take 80% of this data, and then you will train your model with this. And this can be pictures, for instance. Pictures is a good example, and I will show you a code example with TensorFlow from Google at some point in this video right here. So an image is quite good because it can be quite difficult to program something that can look for patterns on a picture and actually categorize a picture. So maybe we want all the dogs categorized placed in one folder, and then we want all of the foxes in another folder. This is image classification, and this is where the supervised machine learning comes in, because what we will do is we will take a lot of pictures, and then we will actually train the machine and say, this is a fox, this is a cat, this is a dog, etc., etc., etc. And then when we have done that enough, then we will actually have a model that we can use to predict other images. And of course, we always need to test. We need to test that model, and that is where it is supervised. So we will actually give it some more images where we know the result. We know which pictures are foxes, cats, and dogs, but we will still feed this to the model, and then we will see in how many situations that this model is actually accurate, and then we will get an accuracy percentage out from this. So this is supervised machine learning. We have an expert that knows what is right and what is wrong, and then we have a model that we will train into getting better and better at classifying images, for instance. Then we have the unsupervised machine learning, and this is a lesser known type of machine learning, because this is usually where you have some advanced mathematical formulas that you will put on top of your data. This means that you will not have categories like you would have with the supervised machine learning. We will not have the dog, cat, and fox categories. We just have some data set. We will have some variables and some results, and then these math formulas will then find patterns inside the data set. They will find, and then they will actually group the input sets through these quite advanced formulas. We will not dig into that kind of machine learning in this video right here. Then we have the reinforced machine learning, and this is a fun one. If you have searched YouTube for reinforced machine learning, then you can actually see that people the programmers can actually write these models that can actually get better and better at playing, for instance, StarCraft, or playing another game like it can also be tic-tac-toe. It can be any game. It can also be action games where you have these shooters where you have your hero that comes from the bottom of the screen, and then you have some enemies that comes in the top of the screen. Actually, the rules, it does not matter about the rules in the game. What matters is that you have a reward system that rewards the reinforced machine learning model whenever it does something good. So that means that if for instance the model chooses to shoot an enemy and the enemy dies, and then it would actually get a +1 reward, for instance, or maybe a +5. And then if it dodges the enemy by going left, maybe by pressing the left arrow key, then maybe you will give a reward of +1. So you can have different rewards for different outcome inside the game, and that is the trick usually with reinforced machine learning, that you have to give the right rewards, and then over time, by letting the computer play the game or do whatever. It doesn't need to be a game. It can also be something like teaching a robot how to walk, for instance. That is also a situation where you could use reinforced machine learning. And this is very powerful, this reinforced machine learning, because you do not need a huge data set to begin with. You can actually build up your data set on the fly. Of course, at some point then you will have a model that is better and better, and that has been trained and seen a lot of situations. So of course that is the trick, to practice, and teach the program, the model, how to behave in different situations. That is reinforced machine learning. I will not show any example of this in this video right here, because this is an introduction to machine learning. So we will focus on the supervised machine learning in just some minutes, in just a couple of minutes. First of all, we also need to see what is a neural network. I have an example of a neural network right here. A neural network consists of different layers, so it's a layered model. And when people talk about that it's actually kind of a black box, then they are quite right. That's because we have some hidden layers in the middle, and that's actually where the magic happens. And what actually happens is that you have some input variables. This could be the grayscale value for each pixel in a picture, and this is the situation we're going to dig into. This means that we can have the blackness of each pixel from 0 to 1 in each pixel coordinates, and that could be the input layers that we have right here. Then the other thing is then we have something called weight or bias. Sometimes it's referred to as bias or weight. This means how important is this line, or this connection from this neuron. Each of these round circles, they are called neurons, and then to the neuron inside the second layer. And as you can see right here, we do not need to have the exact same neurons in each layer. Actually, they will actually most often vary a lot. So we will have fewer neurons, and then maybe we can get some more neurons again. And that is actually the trick to find out how these hidden layers should be which dimensions they should have. So, and that is that is the trick of the supervised machine learning, if you will. So we have a value, and then we have a weight, and those are multiplied together. And then we get a new, and then they're summed up from each neuron that actually points to this neuron right here. So that means that it will be summed up, and then we have a new value in here, and then we will actually have a new value multiplied with weight for each of the connections from this neuron inside the hidden layer to the next hidden layer. And you can have sometimes there can be a lot of hidden layers. Sometimes the more hidden layers that you have, the more precise outcome you can get, the more accurate model you can get. But you also need to be careful not to overtrain your model. Overtraining a model means that you actually have so much. It means two things, because you can actually feed a bunch of images to the model, in different orders. And if you just continue feeding these pictures in different orders, and you do that many times, too many times, then you will get an overtrained. Then you can get an overtrained model that only it is very accurate with the training images. It can almost get you can almost get a 100% accuracy on the training images. But then when you test it with your test images, then you will get a very low accuracy. If you have that situation, then you would definitely then you probably have an overtrained model, and there are ways to handle that. For instance, you can then randomly actually disconnect some of these connections between the hidden layers, or from the hidden layer to the output layer. That is totally up to you. There are different ways of doing that. That's a little bit more complex, and when you come to that problem, because you will probably come to it at some point, then try to search for that subject. There's a lot of good tricks right there. Well, the best trick actually. One trick is not to reiterate the same bunch of pictures that many times into your model. Another trick is to actually cut random connections, like maybe 5% or 10% or 2%. Again, that's something that you have to try with try and error, and then you can get a model that is no longer overtrained. But take the problem whenever it comes. In the beginning, there's a lot of new stuff right here to learn. So we have an input layer, then we have a number of hidden layers, and then we have an output layer in the ends. And in the situation that we're going to look at in some time is that we actually have we have some images that we want to classify. We have some images of shoes, sandals, jackets, etc. We want those. We have 10 categories. That means that we actually have 10 neurons as output neurons in output layer. That means that we have 10 output neurons right there. There are 10 different classes that can be that can be the results. Before we reach the input layer, then sometimes, and that is also a big part of machine learning, that is actually to massage your data. For instance, if you have an image, then usually you would have an X and Y value. So you have an X and Y value, and then you would have the amount of color, the amount of if it's a black and white color, then you would just have one color, like the black color. If you have three colors, if it's red, green, and blue, then of course you would have then you would have three values per coordinate. And when you are dealing with these neural networks, then you have to flatten your data. You have to have one value at a time that comes in to the input layer, and this means that all of these XY values will actually turn into an X1, X2, X3, X4. So they will actually be flattened to a one-dimensional array instead of having multi-dimensional arrays. Fortunately, there's a lot of there are methods to do that makes it very easy for us, and that is exactly where TensorFlow comes in. It can set up this whole flow right here, all of these layers, and it can actually do the compiling and the training, and it can also help us with the testing. So it is not that many lines of code we actually have to write to perform machine learning. It's a very interesting field. Now let us look at the Pac-Man example, just because I actually said that the Pac-Man was actually artificial intelligence, and that's because it imitates human behavior. And just to show that with Pac-Man you actually have 4 different ghosts, and they actually have different behaviors. We have the blinky ghost, that is a very aggressive ghost that would actually just follow and go for the Pac-Man directly. Then we have the pinky ghost, that is the pink ghost that would try to ambush and come in from the side of the cheese. Then we have the inky. The inky ghost will go. It would actually go random places. I've actually forgot. Let's just return to the inky ghost. The Clyde ghost would actually try. The inky ghost is actually quite random. It would just go random places. Then we have the Clyde ghost. It would actually try to stay away. It would actually try to stay away from. Let me just put it right here. The Clyde ghost. It's right there. So the client goes, we will actually try to stay away from the cheese, from the Pac-Man. And so that, let me just see right here, Inky, the cyan ghost will patrol an area which is not predictable in this mode. So that this is actually artificial intelligence because they actually imitate human behavior. It actually seems like they have a mind of their own, even though it's a quite simple programming. Then it is still artificial intelligence, and that's why many people think that artificial intelligence that's only when that's the same as machine learning, for instance. It is not. Machine learning is a subset of artificial intelligence. Enough of that. Now we will go to a framework called TensorFlow. It is a Python framework for doing machine learning, and it is awesome. It's from Google, and if you want to, you can actually use Google Lab. It's a very easy environment that they have, where they have already added all of the needed libraries that we need. And we actually only need two libraries. One is the matplotlib. I'll show you that, and then also the TensorFlow library. So in my situation right here, I have installed Anaconda. And then have set up, and then I've installed those two requirements right here. But there is a lot on TensorFlow.org other tutorials. Then you can actually also see how to do text classification. This means that you can actually evaluate text, and you can actually see if it's a negative text or if it's a positive text. So this could be used to actually filter out trolls, for instance. So that is the basic text classification example. There's a lot of good examples right here. We also have overfit and underfit. That is a very good lesson for solving the situation that we talked about, where you have an overfit model, where you have an overtrained model, where you have which works very good with the images that we are training with, but not with the ones that we are testing with. There is something called the MNIST dataset that is actually part of Keras, so that means that we can actually use this to test and to try out some machine learning stuff. That is 70,000 grayscale images in 10 categories. And as you probably can see, they're a bit small, but you see there are pants, there are blouses, jackets, etc. We have 10 categories of those, and they're all 28 by 28 pixels. So this is a good start because it is very CPU intensive work that is actually being made when you try to train your model, and that is also why it is recommended that you actually use a GPU instead, the graphical processing unit instead. I'll just use the CPU for this demo right here because we are only dealing with 28 by 28 pixels. But if you're dealing with high resolution images and maybe instead of just having black and white grayscale, then you would actually have then you would have three colors, right? You have the three usual colors in some gradient per pixel, and then you would definitely take a long time to use your CPU. While if you use GPUs, then you can get ahead a bit faster. You can also rent GPUs online. You can go to the cloud. Then you can just search for GPUs and machine learning, and then you can actually use those in the cloud. So all of the big cloud providers, they have GPUs available to use. So let us try to look at this MNIST library that we have right here. First of all, I am using Visual Studio Code, so I'm using VS Code, and then I've installed the extension named Python. So I have a Python extension installed right here, and the Python extension pack is right there. It is quite awesome, the extension pack right there, and what is awesome about it is that you actually get this little snake to the left right here, and in this little snake you can choose your environment. It is very easy to set up your environment. You can use Conda, you can use virtual inf, but I recommend you to use Anaconda. And if you don't know how to use Anaconda, then go to Anaconda.org, and then install Miniconda. There's something called Miniconda. You should not if you install Anaconda, then you get a lot of weird stuff that you don't need for data processing. Just download the Miniconda. It's much faster, and you just get the exact necessary instead of the whole package. There's both a community edition and there's also a paid-for version. Of course, use the community edition when you want to practice and see what is possible. Right here with Anaconda, I have created my own environment, and I have done that by writing conda create and then tf demo for TensorFlow demo, and that means that now I have an environment. So that means that I'm not polluting any of the other projects that I'm running where I'm using Python in. I can install whatever I want to into the tf demo Anaconda environment, and then it's only the environment that I actually pollute. I can look at my packages right here. And we should be able to see that I've already installed TensorFlow, but I'll show you how to do that anyway. So here we have TensorFlow, and I also have the matplotlib plots. I need that so I can actually see what's going on inside. I have this matplotlib right there. When you are dealing with Python, then it is a good practice to leave a requirements.txt file in the root, because all of these these dependency managers like Anaconda or virtual environments, they actually they support this requirements.txt. So when you have two lines like this, TensorFlow and matplotlib, then you can ask Anaconda with this command right here. Conda install and then -- file, and then it can actually install all of the requirements from that file right there. There are some of the dependencies are not available in the official Anaconda repository. That's why I need this -c right here. Then we actually look into the Conda Forge repository also. So. Yeah, but if you want to install it on your own machine, then there are a very good tutorial on Google on TensorFlow, and then you can just follow that to install the dependencies. Yeah, but it is quite easy. And if you want to get up and running fast, then use the Google Lab instead. Then you just get a terminal. Yeah, you get a programming environment inside your browser that you can just use per default. I like to have my files right here, and I like to, then I have control over them, so that's why I have installed it locally instead. First of all, let us look at the data. I've created two files. One of them has the purpose of actually looking at the data, and that is the first one. And we have some imports in the top, which are important. We have TensorFlow as TF, so this is just an abbreviation, so it's a bit shorter to write TF than TensorFlow all the time. And then we have NumPy, which we actually don't use in this example right here, but it's an awesome library for manipulating arrays and tensors. And tensor is actually just a set of data. So yeah, it's just a multi-dimensional array, tensor. I'm actually not using NumPy in this situation right here, but in a lot of situations you would have to prepare your data. You have to massage it so it fits the model. The first thing you would actually do is you want to run this as the first line, because this means that TensorFlow actually works and that you have the correct dependencies installed in your environment. Let me just close the other one, close others. And then you want the matplotlib pyplots as PLT, and this is because then you can actually plot the data, you can plot the images, and then we can see what is actually going on. So we have this built-in dataset right here, tf keras dataset.fashion mlist right here, and you just need to know that it's there, of course, and you can also look at the documentation also says that we have a dataset right here, and as you probably already noticed right now, we probably have more than one dataset. We might have more datasets, and that's exactly correct. We in a Keras datasets library, then there's many more datasets that can be used to play around with afterwards. Just go to tensorflow.org and then look for these datasets if you want to try something more advanced. And here we get some training images. So someone has been so nice that they have taken 60,000 images and placed them inside this variable right here. So we have this. Some training images. We have some training labels. A label, that is the result. So the label in this situation right here, that is actually the final, the class name of a set of data. So that means that if we have an image of a dog, then the label would be a dog. And now we are dealing with fashion, so of course if we have an image of a shoe, then the class would actually be shoe. And here we have the classes. We have 10 of those. So we have a t-shirt top, trouser, pullover, dress, coat, sandals, shirt, sneaker, bag, and ankle boot. And there's something else we also need to talk about, that is the test images and the test labels. And it almost sounds like train and test. It almost sounds like the same, but they're definitely not the same. We need to keep those. We need to keep that data totally separated. So that means that we have 10,000 images in the test images, and that is, we use the test images to test our model when we're done. When we're done training our model with the train images, 60,000 images, then we take the last 10,000 images. And then we test how good our model is with those. And 60,000 plus the 10,000, that gives the 70,000 images that was mentioned on the web page just before. But here we have load data, and the first time it will actually take some time to download the data. So the first time it will take a little longer. Then there is something called shape. We can call this the shape right here that will actually tell us how many images do we have. It will actually tell us the shape of the data that we have, how many dimensions do we have, etc. And then we have the length right here. This will actually give us the length, how many pictures do we have right here. Let us just comment this code to begin with right here. I press Control and then the single quote, and then I'll comment all of this right here. Let us just start right here, and then we press play. And I'm using Python 3.9 something, so that is the Python version I'm using right now. First we get the version TensorFlow 2.9.1. Okay, let me just see if I can zoom in a little bit. Yeah. So we get 2.9.1, and then we get the shape. We have 60,000 images. Those images are represented with a 28 times 28 coordinate system because we have x and y values. And totally we have 60,000 images. So that is this line right here. So the shape is very important to understand your data, and of course it needs to be correct, and it needs to be as expected for the input values. The input values need to be we need to flatten it also, but I'll show you how to do that. So and we can do the same now. We can do the same with the train. These are the train labels. We do not want to print those out, I think. Here we have the here we have the train. Let us see how that's. So here we have the images for training, and again we can see here we have 10,000 images, and again they are 28 times 28 pixels. So that is the shape, and again the length, if we call length on it, then we get 10,000 images. Quite cool. Now let us try to see one image, just to prove that this is not just something that I make up, that it actually is an image. If you have a Windows system where you use WSL, then I would say do not use WSL. Place all of it on your Windows machine, also your mini Conda. It will save you a lot of trouble, and it's much faster to use this plotter. It just comes up right away now because I'm running everything on my Windows instance. First I tried inside WSL, and it's very, very slow because the WSL connection between Windows and WSL is quite slow when we are trying to do UI stuff. In old days, you could actually not call UI at all from WSL because it is kind of a Linux server that you get. But enough about that. So here we have one image that is a shirt, as we can see right here, and it has a value between 0 and 250. So that means that when I hold a cursor some random number, then I can see this is x15. So this is pixel x15 and y7. Y starts from the top and goes down right here. And here I can see I have a value of 140. The models prefer a number between 0 and 1. That's just how the numbers actually work, and you could actually come out. It is possible to use numbers that are larger than 1, but it's much preferred that you have a number between 0 and 1 to your input neurons. When you place the value right here, it should preferably be between 0 and 1. That is also because then you don't get an overflow exception, because the variables the numbers can get quite large. So it's also a way to keep the value down, but it is best practice always to get a number between 0 and 1. And here we have a number between 0 and 255. This means that we need to divide with 255. Fortunately, this is very easy, and you can see these two lines right here. These two lines right here, that's actually how we divide with 255. Then I will actually just take the content of all of these tensors, and then I will actually divide that with 255, and then we will have some other values instead. And if I move this code right here, instead of having it right here, then I can just move it right here, because we're actually resetting the training image right here. Let us just take the same picture just to begin with. Now I move the codes. Let us see what happens now. In the plotter, now it is between 0 and 1. So now the value is between 0 and 1 because we divided with that. So that's quite awesome. We still get those weird green colors. That's just how it's plotted. That's okay. If we want the gray colors, then we can try this right here. Here we have the plotter where I print out 20 images. Let us just start with 10. So we print out 10 images right here, and this is math plot. This has nothing to do with machine learning. It has nothing to do with the TensorFlow. This is just math plot. So we can actually print out pictures with the utility math plot that we are using right here. But we need to understand the data before we can actually use it. So let us just try to print out 10 images and see how it looks like after we have divided with the 255. So here we have 10 images. Look quite kind of nice, and if we zoom out, we can also print out more. We can also take 1,000 images. How does that look? Okay, so that was too many. We can maximum print out 25. So let's just do that. There's not enough space inside the plotter. So here we have 25. Here we have 25 images. Yes, looks nice. So now we understand our data. We know that it's images, and we know that we should divide with 255. So here I have the same code. We have the 255 right here. Now comes some other code. We're not plotting any data, because now we know how it looks, right? Know what it looks like. Now we are creating a model. So this is machine learning. So this is an interesting part. So the way to create a model with TensorFlow is to call keras and then sequential. This means that they would actually have each of these layers that we mentioned right here would actually be sequential. So we have to have the input layer first, we have to have the hidden layer, and then we have to end up with an output layer right here. And we can also have a data massage layer. That is why I've added this one right here. So this is the data massage layer. Let us start with that and see how that looks, what that looks like, right? Whoa, we have a data massage layer right here, because this has nothing to do with machine learning, except for that it actually massages the data. So this is, here we flatten out the data, so we'll actually say that we have an input shape of 28 times 28, and then it will take each of the pixel value, instead of those being inside the coordinate, before we have the coordinate maybe 15 and 7, then it would actually take all of the grayscale value, and then it will say, okay, then we have 0.4, then we have 0.21, and then it will take them all and place them in a one-dimensional array instead. That is what flatten does, and that means that then we are compliant with the rule that the input layer has to take one value at a time. It cannot take a multi-dimensional array or tensor. It needs we need one value at a time right here. So that's exactly what we do. Then we create something. We create some dense layers. When you are done with watching this video and when you actually understand what actually happened right here, then there's a lot of other types of layers that you can use, especially if it's more advanced images, because this is a quite simple example. But if you have high definition images, then you want to actually to mirror each image, and you want to, because or else you can only find cats if they sit in the left in the left corner. But you also want the cat to be discovered if it's up in the top right corner instead. You also want the cat to be found if it is on the upside down. Maybe it's airborne, so it's maybe turned only 45 degrees around. And that's exactly what the other layers can do. They can manipulate and twist and turn, and they can mirror the images. And that is also why it takes so long sometimes to train and to run a model. That's because you have all of those weird layers in between. But in this situation right here, it's quite simple. The dense layer, that is the most simple layer when we are dealing with machine learning. And here, this is a number of neurons right here. We can actually say that we know that the input data is 28 times 28. So let me just get a calculator right here. 28 times 28. That is 784. So we have 784 neurons in our input layer, 784, and we can actually choose whatever number we want to. And this is just trial and error. Sometimes it is better to have something that can be that can be divided by 2 or multiplied by 2, and then it gives the next layer. We can just have 2 layers. We can have 3 layers. Let us just have 2 layers to begin with. Then we have something called activation. That is reload. That is something to do with the math behind. And feel free to read up on it. There's plenty of math to actually read up on afterwards. There's also something called the optimizer, which is ADAM right here. That is how to calculate those weights and biases that we have right here. To begin with, just ignore it and just think, okay, this is optimizer that will actually try to optimize this weight for each neuron connection that we actually have. And the same with reload to begin with, just ignore it, and then when you understand what machine learning, the supervised, when you run this example sometimes, then try to read up on it, and then you can see the math. That it looks nice. It is some wild formulas, but you can understand the meaning behind the formulas at least. I think that is good afterwards. So, and the same right here. Here we have something with the losses. So this is the loss that is calculated from a sparse categorical cross entropy function. And again, don't put too much in this word right here. It's just math. So it's advanced math, and there are other ways of calculating loss. There are other ways of calculating optimizer to run the optimizer. The most famous one is ADAM. The most used one is ADAM. Then we have the metrics. That is important. This is what we want to measure, and that is the accuracy. We want to measure the accuracy for how accurate is our model. How many times is it right when it actually when it says this image is a shoe? How many times does it put it in the shoe category? How many times does it by accident put it in the sandal category instead? This is the accuracy. And if it's all by random, then we would have an accuracy of 0.1, which is 10%. 0.1 is 10%. Because we have the accuracy is between 0 and 1. So that means that if we have 0.1, then it's totally random. Then it's like we were just using a dice. So then and if we have anything above that, then of course we're happy. That is not totally true. We should have something around 90% before we are happy, before it is actually applicable and usable. And of course, the closer to 100%, the better it is. Then we have the model fit. This is where, so first we compile the model, and the compilation of the model, that is where this information that we have up here, it is actually just being compiled to something that can then be trained afterwards. So compile just means prepare this model for being able to be trained afterwards. So then we have the training images, the training labels. Remember the labels, that is just the result. So we have some images, the result, and then we have some epochs. Epochs is important. And now I'll just set this to 10 to begin with. This is the number of times where we shuffle our data set and then we put it into the model again. So that means that we take all 60,000 images, then we shuffle, then we put them into into the machine again, and then we see which result do we get there. And then we do that 10 times, shuffle 10 times. And if you shuffle too many times, if you have too many epochs, then you get an overtrained model. So don't, yeah. And in the end, you can actually see that the accuracy improvement from each epoch that we run through is actually getting lower and lower. And then that means that it's actually just waste of time also to run too many epochs. Here we have the loss. Here we have the accuracy, and then we can actually print out the accuracy right here. So test accuracy. This is actually this is the accuracy on the test images. So this is the result. So first we are actually training. Here we are training train the model. So first we train the model like that. Okay, first we compile the model. So that means prepared for being trained, and then test the model against against test images. And this is why it's called supervised machine learning, because we are supervising. We give some images where we know the result, but we want this model to tell us what the result is, right? Verbose, this is just how, verbose in the log output we want it to be. Then we have a probability. Then we have something else, and I think I want to save this for. We have done a lot of things right now, so let us just stop here and then run the program to begin with, just to see what happens, and then we can run then we can continue afterwards. So, okay, so what happens now? So here we have epoch 3, epoch 4, and in the end we can actually see accuracy now. Well, accuracy is close to 90%, and this is just accuracy on the training data. It's not on the test data. So this is on training data. Accuracy we have that the model can actually, So that is the accuracy on the training data, and the accuracy on the test data will almost always be lower. It can be higher if we are lucky, of course, right? Then it can get higher, but usually it will be lower than on the training data, because you have much more training data than you have on the test data. But it can actually also be higher. But here we have the test accuracy, and that is 87%. So that means that 87% of the time, then we are actually we are calculating the correct class with the model that we have created right here. So, and now it comes to the next code, because that is actually where we have something quite interesting, because we can actually get our predictions out like this. So that means that we can actually get our probability model right here, and then we can actually predict all of the images. So this means that try to make a prediction. And let us just look at a prediction for one image. So this is just, then we get a prediction for one image, because we do not get the result from this. It's not from a prediction. It's not just that this is a shoe, for instance. We have to. This is all math, right? So we will get a probability for this as being a shoe. We might have 1% chance that this is a shoe. Then we might have 90% chance that this is actually a jacket. Then we might have a 0.0001% chance that this is a sandal. And then, of course, we actually would like the largest number. If there's 90% chance that this is a jacket, then this probably is a jacket. Then we want to say that it's a jacket. And that's why we need some Python code to tell us that. First of all, let me just show you out the prediction for one image right here. So, again, we run. Ten epochs, and here we have one prediction for image 1. So we can see right here e minus 0.06. That means that there are 6 zeros in front right here. That means that it's 0.00001. So that's probably not it. And here there's 7 zeros in front. This is very low number, 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 very low number. The largest number is actually this one right here. There's actually 0.9. There's only one zero ahead right here. There's 0.98% that this is the last class. And the classes, we have them right here. This means that this is actually an ankle boot. So with 98% chance, This means that this is an ankle boot. We want to get this out with some Python, so let us do that. We want to print out which class it is, instead of us having to look at all those weird numbers and then see which number is the highest one. Then we want Python to do that for us. So we get 40 images out, and then we say, this is the templating way in Python, and then we are calling a format function right here. Every time we have a curly bracket, then that will be replaced with a variable. Here we have the image number. Image number, that's just an integer from 0 and up to 40. If you're not that used to Python, then this is how to create a for loop for, and then you always use range to set the maximum number like this. So here we have the image number, so this, and then we have the class name right here. And here we actually use NumPy here. This is where we use NumPy. Look, we use NP. We go up in the top, then we can actually see that this is NumPy. This is an awesome library for handling and for manipulating data in general, but especially arrays and tensors. It is awesome for that. So here we have an argmax. That means it will take the maximum predicted value. So it will actually take the index for where it is. It will find the index for where the largest number is present. So, and then we will get the class name right here. And then we will also get the class name from the test labels. So this is the real value. This is what the expert says that it was, right? So that we have the result because this is supervised. This is supervised machine learning. So we have the result. So this is a real result. And then we have the predicted result with our model. And this is also what I print out right here. So we say class name, and then we say real class name after that. Let us run this code and just see how it runs. And if you don't understand all of this, then do not be frustrated. Just go to TensorFlow.org and then try out these examples yourself. At some point, you will actually get the idea. It is quite difficult to begin with. There's a lot of math, and there's usually coding is something like if then. Yeah, pick something up from the database, call a service, expose something as a REST service. But this is a different programming field when you come to machine learning. It is something different. It is something totally different. Yes, that I can definitely say that. You need to, the math skills is being challenged a bit. So that's how it is. Okay, so here we have image 0. That's ankle boot. Ankle boot. That was also the real one. That was the real results, and we can go. We can continue trousers, shirt, trousers, coats, shirt, sandal, sneaker, coats, sandals. Oh, so here we have at image 12. Then we get the first error. We think it's a sandal, but it's actually a sneaker. You can say sneakers and sandals look a lot alike. So let us try to continue a bit. Oh, pullover and coat, again, they look a lot alike, right? So that's image 17. Let us try to print out image 17. We thought, our model thought it was a pullover, but it's actually a coat, so we can actually print it out. So let us go look at the data and print out image 17. And that is the test images that we want out. We want image 17, and this is index that we are using. So when I say image 17, it's actually image 18, but it's image with index 17, and then I can just comment this one down here. So let us see image 17. What was the problem with that image? So is that really it's a coat? It is really a coat, but we thought it was a pullover. I can see why it looks like a pullover. I can definitely see why this looks like a pullover, right? So I think that I would actually excuse our model and say that that's quite good. Of course, we can always optimize, and this here as the last thing that is optimized. One optimization is to add the number of epochs. Another optimization is to add more layers. Let us just try to do that. And again, this is trial and error. I'm going to outcomment all of this right here. We are only interested. What we're actually only interested in is the test accuracy that we get right there. That is the that is the performance. How well is our model? So now we're running 15 epochs because I increased the number. And we can see that the accuracy, okay, it actually continues up a bit. So then the number of epochs, that was quite good that we added that, I think. It could also be that we added an extra layer. Test accuracy, we actually went down on the test accuracy, didn't we? It's around the same, the test accuracy. I hope you liked this video. If you did, then please take the time to like, subscribe and hit that notification bell because we have a lot of cool stuff coming up. Bye!